Okay, so last time we talked about the injective and surjective functions, and with different examples. Uh, we have learned this before, but we just uh, extend the uh, the concept into uh, in terms of all the pairs or relations of functions. And especially we talk about quite a bit of piecewise defined functions. And this is usually a little troublesome for people. But the thumb rule is you usually need to separate cases based on the definition of piecewise defined functions. And once that is done, then you can discuss case by case. So that's the key. In this section 3, which is unit 26 or part 26 in the book, we're going to talk about the composition of functions, and this is not new to you. If we start from an example, suppose we have 3 sets, A, B, and C. Set A has 4 numbers, 1, 2, 3, 4, and set B has 3 numbers, 5, 6, 7, and set C has 4 numbers, also 8, 9, 10, 11. And we define 2 functions, f from A to B and g from B to C in the following way by ordered pairs. So f maps 1 to 6, and 2 to 5, 3 to 7, and 4 again to 6. And then G is defined from B to C, so it maps 5 to 8, 6 to 9, and 7 to 10. Okay, so just to remind you again, a function doesn't have to be one-to-one. Like in the first function f is not one-to-one, and it doesn't have to be onto in the second function g. 11 is not in the range of g, so but that's perfectly fine. The domain doesn't have to be the same as code. The range doesn't have to be the same as the codomain. So it will make a lot of sense, or much more sense, if you draw the diagram of arrows from set to set of these 2 functions. Then you just draw the arrows from each number in set A to a number in B based on the definition of F, and similarly, you draw the arrows from set B to set C based on definition of G, function G. And then now, if you forget about the set B and just look at the input on the left from set A and the output in set C, you're going to see 1 maps from 6 to 9, so you can draw arrow directly from 1 to 9. So after a sequence of these 2 functions, 1 in set A maps to 9 in set C, and 2 maps to 5 in B, and 5 maps to 8 in set C. So 2 maps from A to 8 in C. Okay, and 3 maps to 7 from A to B, and 7 maps to 10 from B to C. So 3 maps to 10 instead of C. And finally, 4 maps to 6 from A to B, and from 6 down from B to C. So at the end, the 4 maps from 4 to 9 from A to C. So if you draw the arrows directly from the numbers instead of AM to the terminal image instead of C, you actually get another function, okay, and that's called the composition of 2 functions. And from the discussion we just did, we know it doesn't, the sequence of 2 functions doesn't map 1 number to 2 numbers from A to C, and each number instead of A as an image instead of C after this sequence. So it is indeed another function, and we call this the composition of F and G, but actually F comes first, G second. So that's G composing F in reading. All right. So this is a composition of 2 functions. So as we just said, if you draw the arrows directly from set A to set C, then you get another function. All right. Okay. So we would like to know more about this composition property. Especially the properties of functions like injectivity and the surjectivity behave on composites of functions. If one of this or some of the functions is injective, and then what is composition of the 2 functions? And if any of the functions is surjective, then what happens with composition of the 2 functions? And this we didn't learn before. We need to have a detailed understanding of this composition. Okay, let's just define the composition of functions formally. As we already learned, the functions defined formally in terms of ordered pairs. So we have 2 functions, f and g, f from A to B and g from B to C. So the composition of G with F, reading as G circle F. Okay, so it means F F operates first and then G. Okay, so G circle F will be from A to C because it maps any of the element instead of A to a element instead of B, and then it maps to element instead of C under G. All right. So after this sequence, then we got the relation. Okay. Well, actually, it's we're talking about the function, but in general, it doesn't have to be a function as we'll see later. So let's just define this relation G circle F. So it will be from A to C. Okay, so and they're all the pairs. So you got a relation is a set of ordered pairs, remember? So G composed F will be from A to C. So the ordered pair comes from numbers inside A in the first coordinate, and then element from C in the second coordinate. And they're not arbitrary, obviously. They have to satisfy some conditions. So for any element inside A, in the first coordinate of the ordered pair, then the second coordinate of the ordered pair will be G of FA, because it maps A to F, A and B from A to B. And then on the G, F of A maps to G of F of A. Okay. So F of A is just one element in B. So that's the formal definition of a composition of two functions. It doesn't have to give you a function. In general, we can only say it's a relation. Okay. Well, the coordinates of each other pair has some property, some relation like this. So that makes sense. Okay. So as we just talked about, a composition of two functions that does not necessarily give you another function. So especially when the codomain of F is not equal to the domain of G, and there's no composite function G composite F that is not defined. This is in general, okay. It's not specific. Actually, if more precisely, if the codomain, well, if the range of F is a subset of the domain of G, okay, then it does define a function. All right. And the reason is, if the range of F is larger than the domain of G, then we have some number under F mapped to some number that's not in the domain of G. Okay, so that G is not defined on that number. Then you cannot talk about composition of the two functions. All right, but usually when we define the composition of two functions, we usually intentionally make the codomain of F the same as the domain of G, so that the composition of G with F is always well defined. All right. So let's just see some more examples. Suppose we have this the first the same example as before. I think we just talk about this. Yeah. So that's the example we just started. We have three sets A, B, and C. Just take a look at it again, and then use the formal definition of composition, and see what is G composed F. So A has 4 elements, 4 numbers, 1, 2, 3, 4. B has 3 numbers, 5, 6, 7. C has 4 numbers, 8, 9, 10, 11. So F from A to B is defined as those 4 other pairs, 1, 6, 2, 5, 3, 7, 4, 6. And G defined from B to C has 3 odd pairs, 5, 8, 6, 9, 7, 10. So if you check one by one, you know, then F1 equal to 6, and then you map 6 to 9 in C on the G. So G of 6 equal to 9. So the composition of G with F of 1 is just 9. Or you can write that as G of F1, which is G of 6. Similarly, F2 is 5 and G5 is 8. So the composition of G and F at 2 will be G of F2, which is G of 5 or 8. Okay. And you can do the same thing for 3 and 4. So 3 maps to 7 and then on the F, and maps to 10 on the G, 7 maps to 10 on the G. So 3 maps to 10 on the G. So after the composition, so GF F3 or G compose F at 3 with 10, the 4 maps to 6 on the F and 6 maps to 9 on the G. So 4 maps to 9 under the composition GF. G compose F4 equal to GF F4, which is 9, as we said. So then you have all the other pairs: 1, 9, 2, 8, 3, 10, 4, 9. So we got the same result as we did by drawing the diagram, right? If you look at the 1 maps to 9, 2 maps to 8, 3 maps to 10, 4 maps to 9. Okay, if you look at that, we get the same result, and which it should be okay. So pretty straight. Okay, let's just look at one more example. Very straight also. So suppose the function f from R to R is given by f equal to x plus 1, and the function g from R to R is g of x equal to x squared. Then obviously we got all the domain and the codomains or the set of real numbers, so you can do G compose F and you can do F compose G, because in either case the codomain of one function is equal to the domain of the other function. So for example, if we do G compose F, it will be also from R to R, obviously. By definition, you can write it as G of fx. Okay, but f of x is just x plus 1, so that's G of x plus 1. So what to do, just plug in x plus 1 to the argument in the function g. So the argument x replaced by x plus 1 in g is equal to x plus 1 squared. So that's G compose F, and if we do F compose G, then that's just the F of Gx by definition, or F of x squared. Okay, Gx is x squared. So you just replace x in the function f by, in the definition of f by x squared, so you get x squared plus 1. So you can see if you reverse the order of composition of two functions in general, you're gonna get different results. So composition is not commutative, all right, as we already know. And we saw it before. Okay. In Math 112. Okay, so the next thing is the theorem that shows the although compositional functions are not commutative in general, it is associative. All right. Actually, we talk about that in the other class. Compositional functions is associative, and that's why we can define the operation of a group to be composition of functions like permutations. Okay, so this theorem just to say that if you have four sets A, B, C, and D, and three functions F, G, and H, where F is defined from A to B, G is defined from B to C, and H is defined from C to D. There are three functions. So obviously, you can make a composition of G with F and H with G, and also H with G compose F and G compose with F. If you check the domain and the codomains, we always use the same set from F to G, and from the codomain of F and domain of G the same, so you can compose G with F, and the codomain of G is the same as domain of H, so you can compose H with G, and so on. And at the end, if we compose H with G compose F, it will be from set A to set D. G compose F will be from A to C, right? G compose F, and then you can compose that with H in the front, so that'll be C to D. So at the end, it will be the whole thing will be from A to D. Okay, and similarly, if we do the H compose G, H compose G, it will be from B to D, right? I mean, right, yeah. From B to D. And then you compose it with F. So F from A to B. So at the end, the whole thing will be from A to D again. Okay. So you can see these two compositions, H composed with parentheses of G compose F, and the parentheses of H compose G, and then with F have the same domain A and codomain D. All right. So this is a necessary step. You have to make sure the domain and the codomain are exactly the same if you want to show two functions are identical, which is a step can easily be forgot. And then the only thing, left is just to show that the function values are the same, okay? So we need only to check that for each element in set A, both functions give the same image, and that's easy to show. So, for example, if you compose G with F first, and then compose that with H in the front, and by definition, it's just a H of G compose F of A. Okay, if you think G compose F is another function, right? But then the argument of H is just decompose F A at A. But by definition, the argument is G of FA. So at the end, you get H of G of F of A. And similarly, if you do the composition of H and G first, and then you compose with F, by definition, you're going to map A to F of A in B, and then you map that by H compose G. So this time you just view F of A as an element in B instead of B. So then, by definition of composition of two functions, that's just the H of G of that element in B, which is F of A. So you can see at the end, you got the same thing for these two different compositions. So they do give the same image. So that means these two compositions are identical. Okay, so that proves the associativity of composition of functions. Important theorem result. All right, so you can easily understand why that's the case when you draw the diagram like before. So here we have four sets, A, B, and C, D. So A maps on the F to B, and then B maps on the G to C, and then C maps on the H to D, right? Okay. So the two different path of composition are like this. Okay. If you compose G with F first, then it means you just have a mapping from A to C directly. All right. But they map the, if you start from the same element in set A, then you map to a unique element in set C, because F and G, H, they are all functions. Okay. And then you map from C on the H to D. Okay. So so that's the path on the top. Okay, G compose F is just one mapping, right? From A to C. But you can do it in another way. You can map from B under the mapping of G compose G to D. Okay, so this time you just mapping B to D directly by the composition of H and G. Again, it maps to a unique element in D, and then you map F at the back, actually. So from A to B. So at the end, you map the element from A to a unique element in D, the same as the first path of composition. So then these two paths of compositions gives the same mapping, all right? From A to D. Again, because F, G, H, they're all functions, so the mapping is unique. Okay, so these two path, we usually call these two path or commute. Okay, commute, but it doesn't mean you should not you should not confuse by the commutative properties. It's just the two diagrams are commute. Okay, in more in algebra groups. Okay. All right. So as we just said, this is called the associativity of function composition, so that we can define a group under this operation, like the permutations. Each permutation is regarded as a mapping, right? It is a one-to-one correspondence from a set to itself. Remember, that's a permutation. So it's a mapping, and then if you do two mappings, then you can think that as a composition of two mappings, two functions. So then there's a problem of associativity, and fortunately, because we have this associativity property functions, we can do permutations, in group. That's a essential requirement in groups, associativity. All right. And there are different kinds of associativity in algebra. As in simple cases, we can think of addition of numbers, and the multiplication of numbers. They both have the associativity, but not only that. Matrices, matrix multiplication also has the associativity property. If you multiply three matrices A, B, and C, if their multiplications are defined, okay, so that requires some the dimensions of the matrices. So anyway, if that those multiplications are well defined, then the associativity also holds. So namely, if you multiply three matrices A, B, and C, you can either multiply AB first and then multiply with C, or you can multiply B and C first and then multiply A in the front. You get the same thing. And it turns out that all this kind of associativity has some relation. It's just one manifestation of the function composition. All right. So it does have some underlying reasons. Anyway, so that's that. Okay, the next thing is called the identity function. We talk about it in the other course. Pretty simple, So for any set, you can define the identity function from the set to itself by mapping any element in the set to itself. Okay. So it's written as ID sub set A. Okay. So it maps A, the argument is A, and the function value is A. Okay. So for each of element A in set A. So for example, in terms of the ordered pairs, any function is ordered pairs. Any relation actually is ordered pairs. It's set of ordered pairs. So obviously the identity function, because it's a function, so you can always write that ordered pairs. In this case, very simple, it just maps each number to itself. So the first and the second coordinate in all the pair are always the same. Okay, so 1 map to 1, 2 to 2, 3, 3. So we got 3 ordered pairs. If the set A is the set of 3 numbers, 1, 2, and 3, Similarly, if set B has five elements R, S, T, U, and V, then the identity function on B is just this all the pairs, the set all the pairs of R, S, S, T, T, U, U, V, V. Okay. And it does make sense, you know, why do we need this kind of thing? Since we are already know the groups, you can see why, because we in a group we need the identity, right? Under the operation, we need the identity so that under operation it does not change. And especially in this case, you know, the identity function, identity mapping, you know, if the operation defined in the group is the function operation or mapping, then we do need this identity element in the group, which is the identity mapping. And you know, we talk about the permutations, especially. All right. Well, if you have an identity function and another function, obviously the composition of the identity function with another function is just that function itself. It's pretty easy to understand, but it's also easy to prove. So suppose we have two sets A and B, and we define a function f from set A to set B, and then you know, if you compose the identity function on B with f, you get f itself, and if you compose f in the front with identity function on A, you got f also. So this is exactly what it means by the identity function, you know. It should not change anything if you do the composition of an identity function with any function. It should not do anything actually. Okay. So this is very easy to understand. So how do you prove it? So again, first you have to show that these two have the same domain codomain. So for example, in the case 1, we need to show that the identity composed F and F have the same domain, the codomain obviously that's the case because F is from A to B, then and IDB is from B to B. So at the end, IDB composed F will be from A to B, right? And that's the same as you know, F domain codomains. And then we just need to show, you know, this IDB composed F and F give the same same function value. So just choose any arbitrary number in set A, and if you do mapping from A to B, then f of A obviously will be in B because f is a function. And so then what happens if you do the composition of IDB with f? By definition, it's just IDB of f of A. Okay, if the argument is A in the set A. But what identity function maps out is just f of A itself. If we think fa as one element in B instead of B. Okay. And that's exactly the same for f. F just maps a element inside A to f of A, right? So so we have the first result, and it's similar. You can easily show the second result. So so these two combine to tell us the identity function does not do anything for a function. One is from the left, one is from the right, and both are needed in order to show that. You know, you need to show that both left and the you know operation from the left and the operation from the right to see the composition of another function give the same the same function. Okay, and just like when you show a inverse function, you need to show from the left and from the right. Okay, as we're going to see that later. So I guess we just stopping here and we'll continue on Wednesday with this section. Any questions? I think everything is easy to understand, but we just have a little discussion in more depth about this composition. I have no question, then we're done today.